prepare yourselves for an enormous calamity of phenomenal extents. Betelgeuse, the red Goliath star balanced on the edge of our cosmic system, is conveying dismal messages through the universe. Utilizing the James Webb Space Telescope, cosmologists have uncovered something significantly disturbing about this titanic heavenly body. As famous astrophysicist Brian Cox gives a grave warning, the question looms: are we on the cliff of witnessing a horrendous cosmic explosion blast that could forever change the night sky as we know it? We must dive into the grand tapestry of the universe, where stars are born, live, and die in spectacular fashion. One star has recently captured the imagination and concern of stargazers and the public alike. Betelgeuse, a red supergiant of enormous extents and age, situated prominently in the constellation Orion. Its distinctive ruddy tone and variable brightness have long been a source of fascination, but recent developments have intensified interest in this divine giant. As we explore the nature of Betelgeuse, we find ourselves on the cusp of a potentially great event in the life cycle of this star. But what could these changes in Betelgeuse imply? Are we witnessing the prelude to a cosmic event of unimaginable scale? Betelgeuse, multiple times larger than our Sun, is a stellar behemoth. Its epic size is almost beyond human comprehension. Imagine a star so large that, were it to replace our Sun, its surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its heavenly embrace. This colossal size not only attests to Betelgeuse's physical attributes but also reflects its stage in the stellar life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a stage characterized by expansion and cooling after a life spent fusing hydrogen into helium in its core. But what about the age of Betelgeuse? This star, believed to be around 8.8 to 8.5 million years old, is relatively young in human terms, yet ancient in the context of stellar lifetimes. Its current red supergiant stage is the culmination of millions of years of stellar evolution, a period marked by dramatic changes and processes that have transformed it from a hot blue star to the red giant we see today. The life cycle of stars like Betelgeuse is a tale of transformation, driven by the relentless forces of nuclear fusion and gravity. Betelgeuse's distinctive ruddy tone is another indication of its current stage. The red color results from its relatively cooler surface temperature compared to other stars like our Sun. While the Sun's surface temperature is around 5,500 Kelvin, Betelgeuse's cooler surface registers temperatures around 3,500 Kelvin. This cooler temperature allows Betelgeuse to emit light at wavelengths that give it a red appearance. But this color is not just a visual trait. It provides clues about the star's physical state and the processes occurring within its vast gaseous domain. Adding to Betelgeuse's mystique is its historical color change. Ancient Roman and Chinese writings suggest that about 2,000 years ago, Betelgeuse was yellow. It was only in the 9th century that Arabic scholars first described it as red. This color shift over human history is not just a detail in the annals of astronomy but a clue to the star's evolutionary path. The variable brightness of Betelgeuse is another intriguing aspect. It's a semi-regular variable star, which means its light periodically waxes and wanes. This variability is a characteristic dance of luminosity that has fascinated astronomers and sky watchers for centuries. Typically, Betelgeuse undergoes a 400-day cycle along with a longer cycle that spans around 5 years. These cycles have been recorded as far back as 1836 by Sir John Herschel and possibly even earlier in indigenous oral traditions. However, what makes Betelgeuse truly enigmatic is not just its changing brightness but its irregularity. Unlike many stars that follow a predictable pattern, Betelgeuse sometimes deviates from its rhythmic dimming and brightening, hinting at complex and less understood processes occurring within its massive structure. A recent remarkable discovery caught the attention of cosmologists and astronomers worldwide with a sudden and dramatic change in its appearance, an event now widely known as the Great Dimming. In late 2019, the red supergiant Betelgeuse, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to dim mysteriously. The star's dimming was so pronounced that it started losing its luminosity at an average rate of 0.01 magnitudes per day, reaching its lowest brightness in February 2020. Betelgeuse, usually visible to the naked eye even in light-polluted areas, became noticeably fainter, a change observable even to amateur observers. However, there's one issue with trying to monitor the activities of Betelgeuse: the time paradox. When we look at a star like Betelgeuse, we are not seeing it as it exists today, but as it was in the past, due to the time it takes for light to travel to us. In Betelgeuse's case, at approximately 725 light-years away, the light we see today left the star nearly 7 centuries ago. This delay makes it challenging to predict and monitor sudden changes in a star's behavior, as we are essentially peering into its past. The Betelgeuse dimming event served as a reminder of the inherent difficulties in real-time astronomical observations and the limitations of our understanding when dealing with the vast cosmic scales and the time paradox they present. The unfolding of Betelgeuse's celestial drama was closely monitored by Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team. They used the Hubble Space Telescope to investigate the behemoth star as part of a 3-year study to monitor variations in Betelgeuse's outer atmosphere. These observations offered a unique insight into the dynamics of a variable star like Betelgeuse, which continuously expands and contracts, causing fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed the researchers to probe the layers above the star's surface, which were heated partly by the star's turbulent convection cells. Further analysis of the Hubble spectra, taken at different points throughout 2019 and 2020, helped in measuring the movement of material in Betelgeuse's outer atmosphere. In particular, the spectrograph focused on magnesium-2 lines, which are indicative of the star's atmospheric conditions. These observations showed material moving at speeds of around 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually extended thousands of miles from Betelgeuse and was the precursor to the dust cloud that led to the star's dimming. Dupree and her team estimated that about twice the usual amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the outburst. This mass loss was significant, especially considering that Betelgeuse, like all stars, constantly loses mass but at a rate far greater than that of our Sun. The scale of this mass ejection and the subsequent dimming sparked discussions among astronomers about whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, around 725 light-years from Earth, adds to the intrigue, as any such explosion would be visible from Earth and provide a rare opportunity to observe a supernova up close. But the question remains: what does this dimming event foretell for Betelgeuse's future? Is it a sign of an impending supernova or merely a dramatic episode in the star's long and complex life? Several theories have been proposed to explain this sudden transformation. One dominant theory suggests a progressive process in the supernova explosion sequence, a hypothesis that gained traction due to the widespread belief that Betelgeuse is nearing the end of its life. Another popular theory involved dust, possibly from the star itself, darkening our view. Betelgeuse, like other red supergiants, is known to shed material, and it was thought that this material could form a dust cloud thick enough to diminish the star's light from our perspective. A third explanation considered changes in the star's photosphere, the visible surface layer, which could affect its apparent brightness. In-depth analysis using various observational methods helped unravel this mystery. Spectroscopic studies showed a drop in Betelgeuse's effective temperature, suggesting the dimming could be due to a large dark spot on the star's surface. This theory was supported by the observation that Betelgeuse's temperature dropped by about 170 Kelvin around the time of the dimming, pointing to massive changes on its surface. Ultimately, the key to understanding this rare phenomenon came from humanity's sentinel in space, the Hubble Space Telescope. Hubble's observations revealed that the dimming of Betelgeuse was most likely caused by a massive ejection of hot material into space. This material formed a dust cloud that obscured part of the star's surface, effectively reducing the amount of light reaching us from Betelgeuse. The dust cloud was believed to have formed from extremely hot plasma, which erupted from a large convection cell on the star's surface and then moved through its hot atmosphere to the cooler outer layers. As it cooled, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, were crucial in piecing together the timeline leading up to Betelgeuse's dimming. These observations captured signs of dense, heated material moving through the star's atmosphere in the months preceding the dimming. In December 2019, Several ground-based telescopes also observed the star dimming in brightness, particularly in its southern hemisphere. This material, initially more luminous than the star's usual brightness, ultimately led to the formation of a dust cloud as it interacted with the cosmic environment. The study of this Bow-Shock-Nuth conclusion of the event related to Betelgeuse's cosmic explosion is significant not just for the immediate spectacle but also for its potential impact on our understanding of the universe at large. Here's how this could unfold. Scientific implications and opportunities. The study of such a cosmic explosion would allow scientists to refine their models of stellar evolution. This includes better understanding the processes that lead to supernova explosions and how elements heavier than iron are formed and distributed throughout the cosmos. These processes are critical for the formation of new stars, planets, and even life as we know it. The detection of neutrinos emitted during the explosion would provide crucial data about the extreme conditions within the star's core at the moment of collapse. Neutrinos are unique messengers because they interact very weakly with matter, allowing them to escape the star before any light does, offering a first look at the supernova event. Additionally, a supernova event like this would likely emit gravitational waves, ripples in spacetime caused by the acceleration of massive objects. Detecting these waves would give scientists direct evidence of the violent processes occurring within the star, contributing to the burgeoning field of gravitational wave astronomy. Effects on Earth. While the light show in the night sky would be extraordinary, the cosmic explosion of Betelgeuse, despite its vast energy, would pose no direct threat to Earth due to its distance of approximately 725 light-years. The event would be safe to observe with the naked eye, and its brightness would gradually diminish over weeks or months. However, the gamma rays emitted could potentially affect Earth's upper atmosphere, possibly disrupting satellite communications or causing slight increases in radiation levels. Yet, due to the vast distance, the effects are expected to be minimal. The broader cosmic context. The potential supernova of Betelgeuse would become one of the most studied astronomical events in modern history, akin to SN 1987A, the supernova observed in the Large Magellanic Cloud in 1987. SN 1987A provided invaluable data on stellar death, neutrino emission, and the behavior of supernova remnants. In the case of Betelgeuse, the relatively close proximity to Earth would allow for unprecedented observations across multiple wavelengths of light, neutrinos, and gravitational waves, potentially revolutionizing our understanding of the life cycles of stars and the role of supernovae in shaping the universe. The future of Betelgeuse. Despite the excitement surrounding its potential to go supernova, it's important to remember that predicting such events is inherently uncertain. While Betelgeuse's recent behavior has suggested it might be nearing the end of its life, it could still take thousands or even hundreds of thousands of years before the star actually explodes. In the meantime, Betelgeuse remains a focus of intense observation, with astronomers worldwide eagerly watching for any further signs that it might be approaching its final, dramatic act. In conclusion, whether Betelgeuse explodes tomorrow or in the distant future, its eventual supernova will be an event of cosmic significance, providing a wealth of information that could deepen our understanding of the universe and our place within it.